In this video, we're going to look at some reactions of vinyl and aryl halides. And it doesn't sound terribly exciting, but it turns out there's some really neat chemistry here. But I want to start off by actually looking how one might make a vinyl halide. And we're going to do it by a little bit of roundabout here, but we're going to start with a double bond, and we're going to add a mole of bromine. And then after adding that mole of bromine, I'm going to hit it with some hydroxide. Now what's going to happen? Well, you know what happens when you add a mole of bromine, you get a dibromide. To have that dibromide, you hit some hydroxide. Well, here's a double substitution. Is that really going to be very likely? Nah, hydroxide really wants to do eliminations. And you got various choices down here. You can form a diene. Here I got a bromide double bond here. I'm not sure what the bromine is doing out here on carbon 2. That doesn't look very good. Here I have a triple bond. What do you think is going to really happen? Well, let's go through this stepwise. So we add our bromine, okay? So here's our bromine coming in. The next step, of course, is drawing out that bromonium ion, and then the bromonium ion is opened by on the backside by the other bromide, and we get our dibromo compound. Now the dibromide here is a very perfectly stable compound, but we're going to throw in some hydroxide. So what's the hydroxide going to do? And it's going to go pull off a hydrogen. But which kind of hydrogen? Is it going to pull off a hydrogen on the carbon with the bromine, or is it going to pull off a hydrogen next door? And the way to figure this out is just think about pure acidity. Is that the bromine is not a very electronegative element compared to something like oxygen or chlorine, but it's more electronegative than carbon. So it means that the acidity of this hydrogen on the bromide is actually greater than the acidity over here. So the hydroxide wants to go for well, hydrogen A, it wants to go for that one, and then it's going to do your classic E2 elimination, where in an anti-periplanar way, this hydrogen gets pulled off, forms a new double bond, and the bromide has to leave. And so you've made a vinyl bromide. So this is a perfectly good synthesis for making a vinyl bromide. But now what if we have an excess of hydroxide, we can continue. And now we have to ask the same question as we did before: which hydrogen is actually going to be removed? Are we going to go for A or go for B? Well, let's think about the products in this case. If we remove B, what are we going to get? We're going to get two double bonds in a row. That would be an alene. Aldenes are known molecules. They're somewhat reactive, but generally speaking, they're not as stable as alkynes. And so if instead of moving B, we remove A, it actually will give an alkyne directly, and that's the general reaction that you get. You make alkynes, not aldenes in general in these reactions. And so here you made this nice alkyne. And that's a perfectly good alkyne synthesis. So if you look at this thing as a whole, you could stop the vinyl bromide, you can stop the dibromide, you can stop the vinyl bromide, you can go all the way to the alkyne. Eliminations from these vinyl halides give alkynes. Now, what if it's a ring? Are you going to form a vinyl bromide and then do elimination? Is the same rule going to apply? What would it give? It'd give you the cyclic alkyne. Now, that cyclic alkyne looks pretty unstable to me. It's got what? The alkyne bond is supposed to be 180 degrees, and here it is, it's 120. A does not look very, very nice. These other things, they also look a little bit weird. Are we going to actually do substitution? No, we got to get something else. So let's go through and look at the mechanism. And so we add our bromine, we're going to get this dibromide. Now, the dibromides normally would be equatorial in a ring, but I've drawn them axial. Why have I drawn them axial? Because I know if I'm going to do an elimination, it has to be anti-periplanar. So remember, anti-periplanar means that this hydrogen here that's leaving has to be coplanar with the bromine that's leaving. They're going to form the double bond in the middle. So that hydroxide is going to come down. So you grab that hydrogen, form the double bond there, kick out the bromide. So we've gone to our first compound. Now we're going to do it again, and again it has to be anti-periplanar. So the hydrogen has to be the other axial one up here, and now the bromide can leave down, and that gives us this diene. So this reaction we learned on the previous slide, it's irrelevant because we don't get a vinyl halide at all. So forget this. We don't get an alkyne. We don't get a vinyl halide because this is a ring. You can't do this reaction. So in this particular case, so bromine addition, elimination in a ring gives you a diene, which actually is pretty good. Maybe you're going to do some Diels-Alder reaction. This is a good way to making cyclic dienes for a Diels-Alder reaction. Not such a good way of making acyclic dienes, though, because that one makes the alkynes. Okay, what about the reverse reaction? Can we go backwards? Can we start with an alkyne and go this way? Well, it turns out you can. The first step, anyway, works really well. You add a mole of HBr, and you go back to your vinyl bromide. Now, the regiochemistry in this is determined by the same rules as additions to double bonds. The more stable carbocation intermediate is the wins, but in this particular case, it's a symmetric acetylene, so it doesn't matter which end you add the proton to. In this particular case, you'll get this nice vinyl bromide down here. And so you can go backwards. You make a vinyl bromide from an alkyne. In fact, this is probably a better way of making vinyl bromides than coming this way, because it's just one nice step. Now, what about doing the reaction again? What if you had 2 moles of HBr to your alkyne? First one gives you the vinyl bromide. What will the vinyl bromide give you? Well, for this, you can imagine 2 things. The proton either goes to where the bromide is, and you would make A, which we had before, or the proton would go over here, and we'd make B, where the 2 bromines are on the same carbon. Which one is going to be better? Well, what you have to do is think about the stability of the carbocations. If you add the proton where the bromine is, you'll just get a normal secondary carbocation. But if you do it the other way, if you add the hydrogen to the left over here, you'll make this carbocation with the bromide on it. Now, is the bromine going to help? Well, the bromine it's one of these mixed things. Resonance-wise, it helps because the lone pairs of the bromine can feed into the carbon. Now, bromine's not great at forming pi bonds, but it's enough, it turns out, to turn the tide. And the induction effect isn't that important here because bromine's not that electronegative. So anyway, this is the more stable carbocation. And that simply means when you add second mole bromine, you get this one down here. So you get a dibromide, which is we call a geminal or gem dibromide. Gem means they're on the same atom. So a gem dibromide, 2 bromides in the same atoms. A gem diol is 2 alcohols in the same carbon. It's just one of these words which chemists like to use. So gem dibromide, 2 bromides on the same carbons. These can be useful for certain reactions, and so it's nice to know how to make them. Okay, let's go on to a different subject and talk about the reactions of vinyl bromides or vinyl halides in general. Can you do a substitution reaction on these? Well, SN1 is certainly not going to happen because you're not going to form a carbocation on an sp2 center. So no SN1 reactions. That bromide's just going to leave. But what about SN2? Well, SN2, it turns out, has problems as well. And one of it is you're simply a 4-coordinate intermediate all in the same plane. This would be 60 degrees away. That is not a good idea. That does not work well. You can't really have a backside attack. It's too crowded down here. It just isn't going to work. So it turns out SN2 reactions simply don't work on this. It's not going to happen. So the answer is no, this is not going to happen. But it turns out we can modify those systems so it does. Because what we need is to create a system where we can have a good tetrahedral intermediate, and there is a way of doing that. And that is to add a carbonyl. If you add a carbonyl, it turns out the sulfur will add to this carbon perfectly well. See if you can draw a mechanism. Pause the video. See if you can work this out, because the sulfur is going to add to that bromine, but we're drawing mechanisms where you use the carbonyl. So pause the video, see if you can figure that out. I know you're not pausing the video, but that's okay. We'll pretend you are. Okay, so let me go through it. So the sulfur attacks the bromine. It attacks here. The double bond has to get out of the way, so it moves over. This double bond has to get out of the way, so it moves up into the oxygen. And so what do we end up with? We end up with this intermediate down here. It's tetrahedral at the bromine. So that's no problem. Tetrahedral intermediates are fine. Okay. Then oxygen has the negative charge. So what we've done, we've taken the negative charge from the sulfur, and it's ended up way out here on the oxygen, which is perfectly good. Sulfur is a nice electronegative element. And so this doesn't look bad at all. Now it turns out that, this still is, kind of a reactive molecule. It'd really like to reform the carbonyl. And it does that, of course, by simply bringing the electrons back, doing the reverse of what we did up here. But bromine is a better leaving group than sulfur. And so a bromide is going to be kicked out. So we bring it back, we kick out the bromide, and we've done our net substitution. So this reaction is called an addition elimination mechanism. We've done first an addition of our nucleophile, formed a real intermediate, and then then we've done an elimination, and the leaving group, which was the original group there, leaves. So it's a two-step reaction with a tetrahedral intermediate, which is a very important part of this whole thing. And the reason the tetrahedral intermediate is stable is we've parked the electrons out here on the oxygen. And so getting those electrons onto that carbonyl oxygen is the key to making this reaction work. So this is a substitution reaction which takes place by addition and elimination in an alkene. Okay, so let me go back and we'll see if what about doing these things with an aryl halide instead of a vinyl halide. And will this work? Well, direct attack of that bromide. Are you going to? I'm missing a slide. Sorry. Oh, wrong story first. What about eliminate? I want to do my elimination first. Methoxide. Well, can methoxide eliminate a mole of HBr? This is like we had a little bit earlier with the cyclohexyl ring. Well, if you do this directly, what are you going to make? We have the same exact problem as you had before. You're going to form this triple bond in this ring. And that looks reasonably sick. So it does seem a little bit silly. So does this reaction work? Well, the answer is no. But again, it turns out, I'm kind of leading you up to something. It turns out that, look at C down here, what if we use a really strong base? Methoxide is pretty strong, but what if we use a base which is stronger than methoxide? Well, we'll come back to this in a little bit. It turns out that there's some fireworks coming. So now back to my substitution. Sorry, I got out of order. So our methoxide, can we do this simple substitution? Well, I mean, again, we know that the aromatic ring is fairly electron rich. After all, you just spent a whole chapter on electrophilic aromatic substitution. But now instead of using an electrophile, an acid, we're bringing in a base. And this base does not want to attack that ring. And the reason is there's no place to put the electrons. Because if you just attack at the carbon of the bromine, you just have to have negative charge on a neighboring carbon. And that isn't going to happen. It just doesn't work. You can't get away with it. But what if we do the same trick? What if we have a place to park the electrons? And how would we do that? We would do it by putting on an electron acceptor group. So let's next door to that methoxy put on an electron acceptor group. And we'll use a nitro group in this particular case. So now it is going to work because the methoxide is going to attack the bromide. And what are we going to do? We're going to push these electrons onto the nitro group. And we do it this way. And we get this tetrahedral intermediate, which has the electrons parked out onto the nitro group. This is a perfectly good intermediate, and it's good enough to make the reaction work. And so again, the electrons just come back and kick out the bromide, and we've done our substitution. So this is nucleophilic aromatic substitution. We have done a substitution at the bromide, but it only works because we have a electron withdrawing group to stabilize the tetrahedral intermediate. Now, I've drawn it with the nitro group ortho, and as you probably expect already, it would also work at nitro, and you can do that as a homework exercise. You put the nitro group down there in the para position, it'll work just fine, but meta is going to get you in trouble. Here's another example, and again, if you want to stop the video and work these out, what you'll find is a very similar mechanism. The methoxide is either going to attack the carbon here, or it's going to attack the carbon here. And in both cases, what you want to do is push those electrons toward that carbonyl. Carbonyl is the electron acceptor group. And it turns out, in this particular case, if you look at the para one, you get a nice tetrahedral intermediate with the negative charge on the oxygen. And this is all nice and fine. And in fact, the fluoride really even helps in this particular case, because the fluoride, as turns out, in these nucleophilic aromatic substitution reactions, the fluoride is a great leaving group. And the reason it's such a great leaving group is not because the carbon-fluorine bond is easy to break. In fact, it's not. But what makes the reaction, what makes fluorine good is it speeds up the reaction because it stabilizes this intermediate. And so it's I wouldn't call it the best leaving group, but it's the easiest group to substitute because of the stability of the 4-coordinate intermediate, simply because the electronegativity of the fluorine helps stabilize that negative charge, which is the feature of these tetrahedral intermediates. They have this negative charge. Okay, so that's kind of fun chemistry. All right, meta does not work. Okay, but look at this. This reaction works even though it doesn't have electron withdrawing group. Now, this is pretty bizarre. The NH2 minus is substituting for a bromide. So what's going on here? Is it magic? Well, it looks like magic. The first time you do it, you'd think it was magic, but it's not magic. It's a substitution reaction, but it's not a direct substitution reaction, because if we just attack that nitrogen, attack the bromide, there's no place to put those electrons, and it's not a substitution reaction. But it is a substitution reaction. What it is, it's again a two-step process. It actually starts off with an elimination. An elimination, in fact, an E2 elimination. Remember this slide? I said this wouldn't work, but I gave you a clue that what if you used a really, really strong base? Well, methoxide is a strong base, but there are stronger bases, and one of them is NH2 minus. So if we go to NH2 minus, it turns out that this is such an incredibly strong base. It's the conjugate base of ammonia, all right, and it's like 10 to the 8th times stronger than that methoxide, and it is strong enough to go for that proton and do the elimination. And so this will do the reaction just as you say, and you draw the intermediate. Now look at this. We've been talking about how horrible these things look. It does, but this molecule is kind of schizophrenic because it's not very stable because of that triple bond, but it still has the aromatic stability. This is still an aromatic compound because you only count one pair of those alkyne double bonds. So this is still a 6-electron system. The other 2 electrons in the alkyne are in the plane. And so this is still aromatic. So it gives it a little bit of stability, but that triple bond with those distorted bond angles is horrible. So it's a very, very reactive molecule. And one of the things it'll do, it'll react with a nucleophile. And the nucleophile just attacks a carbon, puts a negative charge on the carbon like this, and you've made this bizarre looking species, which of course will immediately pull up a proton off an ammonia molecule, and you'll get your next reaction. Now, if we isotopically labeled this thing, okay, with a carbon-13, let's say we had a carbon-13 end up here, when we formed our triple bond down here, those 2 carbons get mixed up because these are now equivalent. It's not got symmetry. And so in the final product, the isotopic label from the bromide would be mixed up. Half of it would be where the nitrogen, half of it would be adjacent. And actually half of it would be here, a quarter of it would be the right, a quarter of it would be to the left. It would be a better way of saying it. And so this is a really bizarre thing. Now this intermediate is a real molecule. It is called benzene. And benzene can be reduced other ways as well. It's a reactive molecule. You can't isolate it and put it in a bottle, but you can generate it in a variety of different ways, and you do chemical reactions of this benzene molecule. And here's another example of the benzene molecule. If you make this compound with a fluoride and a bromide ortho to one another, you react this with magnesium metal, you form a Grignard reaction, a reagent with the bromide. But it turns out magnesium and fluorine, they like to bond to each other pretty well as well. So it turns out this thing will split out the magnesium halide and form a triple bond. And this is another route to forming a benzene. There's a variety of different routes to forming benzene, and you'll see another one as a problem set. So what if you have something that will react with a triple bond when you generate this? So if you do this in the presence of furan here, what's going to happen? What's the product going to be? So what do you get? Well, what do you know about triple bonds? Well, triple bonds, for one thing, can react with dienes. This is the Diels-Alder reaction. What's the product of the Diels-Alder reaction? Well, you form a six-membered ring, right? And where is it? It's right down here. It's our good old friend A. And so you're actually generating the benzyne, and it is a very reactive alkyne. It's a very reactive dienophile in a Diels-Alder reaction. So that's kind of a fun species. Okay. And so this is the Diels-Alder reaction of benzyne. And this has actually been done with a lot of different substrates. So thank you very much.